Welcome back to the Deep Dive. We have quite the stack on the desk today. We are cracking open Chapter 5 of what is, frankly, a massive piece of research. The book is Accelerate, the study is the State of DevOps Report, and the chapter title is just one word, a heavy word, architecture.
It does sound a bit heavy, doesn't it?
It really does.
It sounds like we should be wearing hard hats or, I don't know, have drafting compasses out on the table.
Exactly. And I have to make a confession right out of the gate here. When I saw that we were doing a deep dive on architecture, my brain went to this very specific kind of traumatic place.
Oh, yeah.
Yeah, I immediately pictured giant, dusty blueprints. I pictured these, hued, borderline religious arguments about whether to use Rust or Go or Java.
Right, the language wars.
The language wars and whiteboards just covered in boxes and arrows that look like a conspiracy theorist's basement.
That is the Pavlovian response for most of us in the tech world, I think. You hear architecture and you immediately think about the stuff.
The stuff, yes.
The bricks, the mortar, the servers, the database schemas, the syntax. You think about these rigid structures that hold the software up.
I was fully bracing myself for a 60-minute lecture on why Kubernetes is the answer to all of life's problems, or maybe why we need to refactor everything into a service mesh. But, and this is why I love doing these deep dives, the source material completely flipped that narrative on its head, like within the first 2 pages.
It really does.
Because, if I'm reading this right, this chapter isn't really about the code at all, is it?
No, and that is the twist that makes this study so groundbreaking. The core argument here, and they back this up with a massive amount of statistical data, is that we've been looking at architecture through the wrong lens.
Okay.
We aren't here to talk about building walls or picking the best technology stack. We're here to talk about breaking dependencies.
Breaking dependencies.
Yeah. The study suggests that the structure of your system, your architecture, actually dictates the performance of the human beings building it. It is a sociological issue disguised as a technical one.
Uncoupling the knot.
Precisely. Uncoupling the knot. It's all about how the shape of the system shapes the people, and then how the people, in turn, shape the system.
So let's jump straight into the hook here, because the study opens with a reality check that I think a lot of us really need to hear. There is this pervading myth in the tech world, and I've certainly been guilty of believing it. It's a mental trap. The myth is that if you are working on a legacy system, the old stuff, the mainframes, the monolithic dinosaurs from the 90s.
The big iron?
The big iron, yeah. The myth is you're doomed to be slow. You're just structurally incapable of moving fast. And conversely, if you're working on a greenfield project, brand new code, fresh slate, cloud native, you are automatically going to be high performing.
The classic newer is better fallacy. It's the new car smell of software development.
It totally is.
We just assume that the age of the technology dictates the velocity of the team. If it's old, it's slow. If it's new, it's fast. If it's COBOL, it's bad. If it's Node.js, it's good.
But the data in this chapter says absolutely not.
It debunks it completely. And this is one of the first big shocks in the source material. They looked at the data across thousands of companies, and they found zero significant correlation between the age or type of the system and the performance of the team.
Wow.
You can have an incredibly high-performing team working on a mainframe from the 1980s.
That seems so counterintuitive. We usually associate mainframes with, people in ties waiting 6 months to release a single update.
That's the stereotype.
Right.
But the data shows you can also have a sluggish, low-performing, miserable team working on a brand new, cutting-edge microservices stack.
Right.
The technology itself is not your destiny. The tools don't save you.
That is wild to me. It feels like finding out a Model T Ford can beat a Tesla in a drag race if the driver and the mechanic know what they're doing.
In a way, yes, but it's more about how the car is put together, not just the engine. It leads us to something we are going to explore deeply today called the inverse Conway maneuver.
Which still sounds like a wrestling move to me.
It does.
Or maybe a chess opening. He's playing the inverse Conway maneuver.
It does have a certain ring to it, but it's actually a strategy that suggests you cannot fix your broken code until you fix your broken organizational chart.
I love that concept. Okay, so here's the promise for you, the listener, today. We are going to explain why adding more people to a software team usually makes it slower. We've all seen that happen, right? The too many cooks problem.
Oh, absolutely.
But how the elite teams in this study actually get faster as they grow, exponentially faster.
That is the scaling paradox, and it effectively changes the economics of software development. It turns the whole mythical man month on its head.
And we're going to settle the eternal debate on standardization versus autonomy. Should you let your engineers pick their own tools, or should you force everyone to use the same list? The answer in the data is, well, it's surprising.
It is nuanced, but the direction is very, very clear.
All right, let's unpack this. Let's start with this system type fallacy. The researchers didn't just guess here. They categorized everything to see if they could find a pattern. They really cast a wide net.
Right. They wanted to be thorough. They didn't just look at, web apps. They looked at a really wide spectrum of system types to see if there was any correlation with delivery performance. So they looked at greenfield systems.
The brand new ones.
Yep. Those are the ones where you don't have any technical debt yet. Everything is shiny and perfect.
The honeymoon phase of coding.
Exactly. Then they looked at systems of engagement.
Okay, so the user-facing stuff.
Yeah, these are usually the apps, the mobile apps, the websites, the pretty stuff that the customer actually touches and swipes on.
The stuff that gets the marketing budget.
Usually, yes. Then they looked at systems of record.
Okay, the heavy stuff.
The heavy lifting. These are the big databases, the critical information storage where if you lose data, the company dies. Financial ledgers, patient records, inventory management.
Got it. The serious stuff.
They also looked at packaged commercial software, so things you buy off the shelf and then customize. They looked at embedded software.
Like firmware.
Exactly, like firmware on a thermostat or the code running inside a pacemaker.
Which is a totally different beast than a website. If a pacemaker crashes, you can't just refresh the browser.
No, the stakes are slightly different there. And of course, they looked at the mainframes, the big iron.
And again, the obvious assumption here, the one we all make, is the cool kids working on the mobile apps or the startups on greenfield projects must be outperforming the poor souls maintaining the mainframe.
That is the assumption. We assume legacy equals lethargy. But when they ran the numbers, there was no significant correlation. None.
So statistically speaking, the type of system you're working on is irrelevant to your delivery performance.
Yes, the data shows that high performance is possible with all kinds of systems. You are not doomed by your platform, and I think this is incredibly liberating for people working in enterprise IT.
Oh, for sure.
You don't have to throw away the mainframe to get fast. You don't have to rewrite everything in the latest JavaScript framework to be an elite performer. You can be elite right where you are.
That's a huge relief for anyone staring at a million lines of COBOL right now.
Yeah.
However, reading through the notes, there was one exception. There was one specific category that did correlate strongly with low performance. Who were the unlucky ones?
The category was custom software developed by another company.
Oof.
Essentially outsourcing partners.
Okay, let's dig into that. I feel like we need to be careful here because we aren't saying outsourced developers are bad at coding, right? That would be a gross generalization.
Correct. This is absolutely not about skill or talent. There are brilliant developers all over the world working in outsourcing firms. This finding isn't about the people, it's about the structure.
The structure.
It comes back to the theme of this entire deep dive, handoffs and coupling.
Okay, paint the picture for me. Why is outsourcing the kiss of death for performance in this context?
Well, think about the logistics of a traditional outsourced arrangement. You are building a feature. To finish that feature, you need a change in the core code. But that core code is owned by a separate company. Maybe they are in a different building. Maybe they are in a different country.
Right. You can't just roll your chair over and tap them on the shoulder.
Exactly. You are stuck. You aren't just walking over to a colleague's desk. You are logging into a portal. You are writing a ticket. You are describing the requirement in text, hoping they understand the nuance. You hit submit, and then
you wait.
You wait. You are dealing with a different time zone, so you might not get a reply for 12 hours. Maybe they reply with a clarifying question. Now you're 24 hours in. Maybe you need to negotiate a contract change in order to get that code written because it wasn't in the original scope. Now you're 2 weeks in. You are not loosely coupled. You are tightly coupled to an external entity.
Right.
You cannot move fast because your hands are tied by a contract and a communication barrier.
It creates a structural wait time. It's built-in latency.
Exactly. It creates a communication bottleneck. And this study is relentless about bottlenecks. If you have to wait for someone else to do their job before you can do yours, you are slow. And outsourcing, by its very nature, almost always guarantees that dynamic. It inserts a wall where there should be a door.
That makes total sense. It's friction. Pure organizational friction. Now, the source material also mentions systems of record. I feel like a lot of managers use that as a shield.
Oh, all the time.
They say, oh, we can't deploy fast. We're a system of record. We hold the banking data. We have to be slow to be safe.
It's a very common excuse. We are too important to move fast. It sounds responsible, doesn't it? We move slow because we care. It sounds like prudence.
Right. It feels like the adult thing to say in the room.
But the data proves this is a false dichotomy. There were high-performing teams managing systems of record. They were deploying frequently and with stability. So using safety or importance as an excuse for slowness doesn't hold water in the face of this evidence. In fact, later in the study, they argue that moving fast actually increases safety because you're releasing smaller changes that are easier to fix. If you release once a year, that release is a terrifying monster. If you release every day, it's just a Tuesday.
So the takeaway from this first section is pretty clear then. It's not what you are building. You can't blame the mainframe. You can't blame the database complexity.
Right.
It's the architectural characteristics of how you build it.
Correct. It shifts the blame and the power back to the team. You can fix this regardless of the tech stack.
Okay, so if the system type doesn't matter, what does matter? If I'm a CTO or a lead engineer listening to this, and I can't just look at my tech stack to know if I'm doing well, what should I be measuring? The study identifies two pillars or metrics that the high performers all shared.
Yes. They distilled it down to two specific statements that high performers consistently agreed with. If you want to know if your architecture is good, ask your team to rate these two statements.
Okay.
Number one, can we do most of our testing without requiring an integrated environment?
Integrated environment. That sounds like jargon. We need to pin that down. And number two,
can we and do we deploy our application independently of other services?
okay, those sound simple, but I feel like there is a world of pain hidden in them.
Yeah.
Let's start with the first one, the integrated environment. What exactly does the source mean by that, and why is it a villain in this story?
The text defines an integrated environment essentially as a staging area, a testing server, where you have to dump everyone's code together to see if it works.
Yeah.
Imagine you have 10 different teams working on 10 different parts of a large e-commerce website. Team A is doing the shopping cart, Team B is doing the search bar, Team C is doing payments.
Got it. Standard stuff.
In a traditional tightly coupled world, Team A can't really know if their shopping cart code works until they merge it with Team B and Team C in a massive staging environment. They rely on the whole system being present to run a test.
It's the potluck dinner analogy. I can't taste my dish until everyone else arrives and puts their food on the table.
And if Team C's dish is rotten,
The whole dinner is ruined.
exactly. If the payment service crashes the staging environment, the shopping cart team can't test their code.
Yeah.
Everyone stops. You get an email saying staging is down, nobody merge anything.
I have lived that life. It is miserable. You're just sitting there.
It's fragility and it's a bottleneck. The source explains that these integrated environments are expensive to set up, they are hard to maintain, but worst of all, they block everyone. If the staging environment is broken because of one team, nobody can test, nobody can deploy.
You are all handcuffed together.
Exactly, and that destroys the flow. You're sitting there twiddling your thumbs, waiting for the environment to be green.
Right.
And that waiting is where the performance dies. High performers don't do that. They design their architecture so that Team A can test their code in isolation. They use things called test doubles or virtualization.
Explain that. Test doubles.
Think of it like a crash test dummy. If I'm testing a car's airbag, I don't need a real human in the seat. That would be messy and unethical. I use a dummy that looks like a human to the sensors. In software, if my shopping cart needs to talk to the payment system, I don't need the real payment system to be online.
Okay.
I can use a test double, a small piece of code that just pretends to be the payment system. It says payment accepted or payment declined, so I can test my cart logic without waiting for the actual payment team.
So I can work completely alone. I don't need the other teams to be ready. I don't care if the payment team's on vacation.
Exactly. You are uncoupled. You have cut the string that ties your productivity to theirs.
That leads perfectly to the concept of loose coupling. The text calls this the holy grail of architecture.
Loose coupling is the goal. It is the defining characteristic of high performance.
So let's list the criteria this study gives. If I'm a listener and I want to know if my team is truly loosely coupled, what should I be able to do?
It's a tough checklist. First, you must be able to make large-scale design changes to your system without asking permission from someone outside your team.
Without permission, that's a big one. No change control board for the design.
Not for the internal design of your component. If you own the shopping cart, you decide how the shopping cart is built. You don't need a committee to approve your variable names or your class structure.
Okay.
Second, you must be able to complete your work without coordinating with people outside the team.
Hmm.
No meeting with the database team just to add a column. Third, deploy on demand. You can push your button whenever you want, regardless of what the other services are doing. You don't need to ask, is it safe to deploy? You know it is.
Okay.
And fourth, fix things during business hours with negligible downtime.
That sounds like a dream for most developers. But I want to talk about the human side of this. We said this episode is about people. How does loose coupling affect my daily life as an engineer? How does it save my sanity?
Think about the alternative. If you are tightly coupled, you spend your life in meetings. You spend your life coordinating. Hey, are you releasing Tuesday? Because I need to release Wednesday. Oh no, you broke the build waiting for approval. That is frustrating work. It's high stress, low value work. You feel like a bureaucrat, not a builder.
It's deployment pain. It's the stomach ache you get on release day.
Exactly. The source connects this directly to burnout. When you are loosely coupled, you control your own destiny. You build it, you test it alone, you ship it, you get that dopamine hit of finishing the job.
Right.
That reduces burnout significantly because you feel effective, you have agency.
It's autonomy. We crave autonomy.
We do. And architecture is the mechanism that grants or denies that autonomy. If your architecture is a tangled knot, no amount of empowerment speeches from the CEO will make you autonomous. The code won't let you be.
That is a profound point. You can't culture hack your way out of a bad architecture.
No. Physics wins. Or in this case, dependency graphs win.
This brings us to a name that keeps popping up in software engineering lore. Melvin Conway. Section 3 is all about Conway's Law.
You cannot discuss software architecture without paying homage to Melvin Conway. In 1968, that's over 50 years ago, he made an observation that is still perfectly accurate today.
What was the law?
Organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations.
That is a bit of a tongue twister.
Okay.
Can we get the explain it like I'm 5 version of that?
The classic analogy is the compiler. If you have 4 teams working on a compiler, you will inevitably build a 4-pass compiler.
Because each team builds one part and they just stick them together in a line.
Exactly. Your software will look like your org chart. If your organization is a hierarchical pyramid, your software will likely be a monolithic pyramid.
Okay.
If your organization is a scattered mess of disconnected squads, your software will be a scattered mess of disconnected services.
So the software is just a mirror of how people talk to each other.
Yes. If Team A and Team B never talk, their code will not integrate well. If Team A and Team B talk constantly, their code will be tightly coupled.
And this leads to the inverse Conway maneuver.
It is a strategic pivot. The idea is, don't just fight the code. If you look at your code and say, we want this to be modular, we want nice, clean microservices, but your team is one giant blob of 100 people, you will fail.
Right.
You cannot write modular code with a monolithic team.
So you have to change the team first.
You have to evolve the team structure to match the architecture you want. If you want independent services, you need independent teams. You basically hack Conway's Law. You change the org chart to force the code to change.
And the source material gets specific about what those teams look like. It says they must be cross-functional.
This is critical. To avoid those handoffs we talked about earlier, where you wait for the database team or the QA team, the team needs to have everyone. They need the developers, the testers, the operations skills, the database skills, all in one squad.
So they don't have to call another department to get things done.
Right. If you have to call the DBA team to change a schema, you have reintroduced the communication bottleneck. You have violated the inverse Conway maneuver. You need to pull that capability into the team so they can move fast.
Now, there is a nuance here that I think is really important, the bandwidth problem. The text mentions we want teams to collaborate, obviously. We aren't building hermit kingdoms where nobody talks to each other.
No, we aren't isolationists, but we need to be very careful about what we communicate about. The text says we want to avoid high bandwidth communication for fine-grained decision-making. Meaning, I shouldn't have to talk to you to decide if I can change a variable name. I shouldn't have to talk to you to decide how I implement a specific function. That should be my decision.
Okay.
We should use our communication bandwidth for the big stuff. What is the goal of the product? How do our APIs talk to each other? What is the strategy?
Save the talk for the strategy, not the implementation.
Exactly. If we are talking constantly about implementation details, our architecture is too coupled. It means my code is so entangled with yours that I can't move without asking you first. That's bad architecture.
The source also drops a warning about service-oriented architecture, or SOA, and microservices. It seems like a lot of companies read microservices on a blog and think, that's it. That's the answer. We'll just split everything into tiny pieces.
It is the buzzword of the decade, for sure.
Yeah.
But the text warns that simply calling something SOA or microservices doesn't work if you cheat.
If you cheat, how do you cheat at architecture?
If you build 10 microservices, but they all share the same database, you haven't uncoupled anything. You've just made your monolith harder to debug because now it's over a network.
Yeah, the distributed monolith. The worst of both worlds.
Exactly. If you build microservices, but you still have to deploy them all at the same time, like, okay, everyone, we're pushing all 50 services at midnight. That is not microservices. That is a disaster waiting to happen.
So true loose coupling requires strict discipline. It's not just splitting the code into different folders.
It is about splitting the dependencies and the deployments. If you can't deploy service A without service B, they are not decoupled, period. It's like saying you have two cars, but they share the same steering wheel. You hasn't really solved the problem, you've just made driving impossible.
This brings us to maybe the most striking visual in the whole chapter, Figure 5.1, the scaling paradox. This is where the business case really lands.
This is where the rubber meets the road for the executives. This is the slide you show to the CFO.
So picture a graph, listener. On the x-axis, the bottom, we have the number of developers. So team size. Moving from left to right, the team gets bigger. On the y-axis, on the side, we have deploy frequency. And note, this is a logarithmic scale, so the jumps are huge.
And the question the researchers asked is, as you add more developers, what happens to your deploy frequency?
Right. And the orthodox view, the common wisdom, quoting Fred Brooks from the Mythical Man Month, is that as you add people, individual productivity drops. Communication overhead eats everything. Too many cooks in the kitchen.
That is the standard belief. More people equals more coordination equals slower movement. It is the death spiral of coordination. If you have 5 people, you can talk easily. If you have 500 people, you spend all day just trying to stay in sync.
Yeah.
You spend more time talking about the work than doing the work.
And when we look at the low performers line on this graph, that is exactly what happens.
It is tragic. The low performers line goes down. As they add more developers, they actually deploy less frequently.
That is painful.
Yeah.
Imagine hiring 50 more engineers, paying those salaries, paying for the recruiting, onboarding them, and the result is that you get slower.
It happens every day in large organizations. You add people, but because the architecture is tightly coupled, those people just create more meetings, more merge conflicts, and more waiting. They clog the pipes. They're tripping over each other.
But then there are the high performers.
The high performers line defies gravity. As the team gets bigger, their deploy frequency increases significantly. It curves upward. It's exponential.
How is that possible? How can adding people make the whole thing faster per person?
It returns to loose coupling. Imagine a swimming pool. If everyone has to swim in one lane, adding more swimmers creates a traffic jam. That is the low performers.
Chaos, kicking each other in the face.
Exactly. But if your architecture is loosely coupled, adding a new team is like digging a new lane in the pool.
Ah, okay.
They have their own lane.
Yeah.
They can swim as fast as they want without bumping into anyone else.
You add a team, you add a swim lane, you add another team, another swim lane.
Exactly. You are adding capacity linearly, or even better than linearly, because the teams are autonomous. They don't have to coordinate. This is the business value of architecture. It allows you to buy speed. If you have a loosely coupled architecture, you can hire your way to faster delivery.
Wow.
If you have a tightly coupled architecture, hiring is just setting money on fire.
That is a powerful, clear-cut distinction. Can you buy speed? If the answer is no, check your architecture.
Precisely. If you throw money at the problem and it gets worse, you have a coupling problem.
Let's move to section 5. Tools. This is always a spicy topic. Standardization versus autonomy.
The eternal battle, the holy war of IT.
In the red corner, we have the corporate IP department. They want a standardized tool list.
Wow.
They want everyone using the same version of Java, the same IDE, the same CI/CD server. Why?
Well, the text is fair to them. There are good reasons. It reduces complexity. If everyone uses Java, you can hire Java devs easily. It helps with licensing costs. You get a bulk discount if you buy 1,000 licenses of one tool versus 10 licenses of 100 tools.
Right.
It simplifies purchasing and compliance.
It's efficient. From a procurement standpoint.
From a procurement standpoint, yes. It makes the spreadsheet look nice.
And in the blue corner, we have the engineers. They want to pick their own tools. They want to use the latest language, the coolest new framework, the specific library that just came out last week.
And the data says the engineer should win.
Really? Total anarchy.
Well, let's look at the finding first. The study found that teams who can choose their own tools perform better, statistically better.
Why is that? Is it just because developers like shiny new toys and are happier?
It's deeper than that. It's about problem solving. Engineers are professionals. They choose a tool because it helps them solve their specific problem best. If you force a carpenter to use a wrench to hammer in a nail, they will be slow and the result will be bad. If you let them pick the hammer, they work faster. The tool fits the task.
And there is a psychological factor too, right? Ownership.
Ownership. If I choose the tool, I am invested in making it work. If you force the tool on me and it breaks, I just blame you. Stupid corporate tool. I disengage.
Right.
I become a victim of the system. If I picked it, I own the outcome.
The text mentions treating internal tools like a product.
Yes. This is a huge shift in mindset. Internal tool teams, the ones effectively making the standard list, should treat the engineers as customers. They shouldn't say, you must use this. They should say, we built this amazing tool that makes your life easier. You should try it.
If the tool is actually good, people will use it voluntarily.
Exactly. If you have to force people to use your tool by decree, it implies the tool provides no value on its own. It might be a bad tool. It implies your tool sucks.
Now, you mentioned anarchy earlier. Does the text advocate for a total Wild West where everyone uses a different language and database?
Yeah.
Because I can see how that would be a nightmare for maintenance.
Right, like, oh, the guy who wrote this in Haskell left, and now nobody knows how it works.
Exactly.
No, and this is the critical nuance. There's a reference to Steve Yeggie's famous rant about Amazon.
The platform rant.
The platform rant. It's legendary. The text uses it to distinguish between tools and infrastructure interfaces.
Okay, what's the difference?
You can let teams pick their libraries, their frameworks, maybe even their language. That's the inside of their house. But you must standardize the plumbing and the streets.
So how we connect to the system.
Exactly. Steve Yedge pointed out that at Amazon, you can't debug anything if everyone runs their service differently. You need a universal standard way to run services. Monitoring, logging, deployment APIs.
So standardize the platform, the container, the way we log errors, but let the team decide what runs inside the container.
That is the balance. Standardize the plumbing so the house doesn't flood, but let them decorate the rooms however they want. You create what Netflix calls a paved road.
A paved road. I like that imagery.
Yes. You say, if you use our standard tools, the road is paved. Deployment is automatic. Security is built in. It's easy. You can drive 100 miles per hour. If you want to go off-road and use something weird, you can. But you have to bring your own machete. You are on your own.
That makes sense. It encourages standardization through ease of use, not through force.
Exactly. You lure them in with convenience.
There is also a bit about security here. Usually security is the department that says no.
The Department of No.
Right. But high performers do it differently.
High performers integrate security into that platform we just talked about. They provide pre-approved, easy-to-consume library.
A Lego brick approach.
Yes. Instead of a security guard stopping you at the door every time you want to bring something in, they give you a pile of pre-checked Lego bricks. These bricks are safe. They've been scanned. Build whatever you want with them.
That speeds things up immensely. You don't have to wait for a security audit if you use the pre-approved bricks.
Exactly. It makes doing the right thing the easiest thing. And that's how you win the standardization versus autonomy war. You make the standard way the easiest way.
So we have talked about systems, coupling, scaling, and tools. This leaves us with one person, the architect.
The person with the title.
Section 6 asks, if we aren't picking tools, because the teams do that, and we aren't drawing rigid diagrams because we want autonomy, what on earth does an architect do? Are they obsolete?
The role doesn't disappear, but it shifts completely. In the old world, the architect was the commander. They sat in the ivory tower and dictated the laws.
Thou shalt use Oracle.
Right. Thou shalt use this specific message bus. Thou shalt not use open source. In the high-performing world, the architect is a servant leader. The text concludes that architects should focus on two things: outcomes and engineers.
Outcomes and engineers. Break that down for me.
Instead of asking, should we use Kubernetes or Mesos, which is a tool question, they should ask, does this decision enable the team to deploy independently?
That's an outcome question.
Exactly. Does this decision help the team test faster? That is an outcome question. The architect becomes the guardian of the flow, not the guardian of the stack. They are looking for bottlenecks.
They are the ones watching out for the swim lanes. They make sure nobody builds a dam across the pool.
Exactly. And they must collaborate closely with the users. And in this case, the users are the engineers.
So the architect shouldn't be a stranger.
No. They need to be down in the trenches, understanding the friction the developers feel. Their job is to remove that friction. If the standard platform is hard to use, the architect needs to fix it, not blame the developers for being lazy.
It sounds like being a town planner rather than a building inspector.
I like that analogy. You plan the roads, you ensure the sewage works, you set the zoning laws so the factories aren't next to the schools. But you don't tell people what color to paint their kitchen. You enable the city to grow without collapsing.
This has been a journey. We started this episode thinking about architecture as this dry, technical, code-heavy topic.
And we realized it is almost entirely a sociological topic. It's about how people work together.
Let's synthesize this for the listener. We covered a lot of ground.
Sure, let's do it.
Point 1. The type of system you have, mainframe versus greenfield, doesn't matter. It's not an excuse.
Correct. No more excuses. You can be elite on a mainframe. You can be terrible in the cloud.
Point 2. The metrics that matter are testability and deployability. Can you test without a potluck dinner? Can you deploy without a committee meeting?
That is the litmus test. If the answer to either of those is no, you are coupled.
Point 3. Loose coupling is the magic key. It breaks the communication overhead curse. It allows you to add people and actually get faster.
The scaling paradox. If
Yeah.
you want to buy speed, you need loose coupling.
And point 4. Let the experts, the engineers, pick their tools. Standardize the grid, not the toaster.
Trust your people.
It all keeps coming back to trust and autonomy, doesn't it?
It does. Technical high performance is deeply rooted in organizational trust. You trust the team to pick the tool. You trust the team to deploy the code. You trust the team to fix it if it breaks. That trust is faster than any control mechanism.
Before we go, I want to leave the listener with a final provocation. We usually end with something to chew on. You have a thought on the inverse Conway maneuver that goes a bit beyond the text.
Yes. We talked about how your org chart dictates your software. But I want you to look at something more practical. If your software is slow, buggy, and hard to release, stop looking at the code for a moment. Stop looking at your Jira backlog.
Where should they look?
Look at your calendar.
The calendar.
Open your work calendar. Look at your meetings. If your calendar is full of meetings with other teams, if you have sync with Team B, integration planning with Team C, deployment approval board, that is your architecture.
The calendar is the crime scene.
The calendar is the reality. Those meetings exist because your architecture forces you to coordinate. You are acting as the human glue for a broken system. Every one of those meetings represents a dependency that hasn't been broken in the code.
Wow.
So the provocation is, how can you redesign your team and your calendar to fix your software?
Delete the meeting because the dependency is gone.
That is the ultimate goal. If you can delete the meeting because the software no longer requires the conversation, you have won.
That is a powerful goal and a great place to stop. Thank you for that. And thank you, listener, for joining us on this deep dive into the hidden human side of architecture. I hope you look at your mainframes, your microservices, and especially your calendars a little differently today.
Keep uncoupling those knots.
See you next time.